Hi there and welcome back. Let us look at a Bernoulli example. In this case, we are required to determine the pump head. We are told that a distillation column is operated at a pressure gauge of 480 kPa. The feed stream from the column is obtained from the storage tank at 500 kPa absolute. A pump is available to pump the feed to the column. The feed liquid and viscosity is given. The pipe that connects the storage tank and the column is 50 meter long and is made from a commercial steel with 49.25 mm inside diameter. And we're also given that the atmospheric pressure is 101 kPa absolute and the feed point from the column is 8 meter higher. The Bernoulli equation says height at point 2, speed at point 2 squared over 2 gravitational acceleration plus pressure at point 2, density gravitational. Subtracting height at point 1 plus speed at point 1 squared over 2 gravitational acceleration plus pressure at point 1 gravitational acceleration should be equated to the pump head, or you can say horsepower, subtracting the friction loss. The first thing I'm going to do is to write down that which we are given. Let's take the reference point to be point 1 and we'll make it 0. Therefore, height 2 will be 8 meters. Mind you, Z is basically the height. Pressure at point 1 is given to be 500 kilopascal. Pressure at point 2 can be calculated, and we can say pressure absolute is basically gauge pressure plus the atmospheric pressure. And this is 480 kilopascal plus 101.325 kilopascal. If you punch this into your calculator, you should get a pressure of. We are also given the relative roughness to be 0.0000045. We are given the diameter of the pipeline to be consistent at 49.25. It's in millimeters, so you can just say to the power of -3 to make it just 1 m, which is meter. We are given the viscosity 0.5 times 10 to the power of -3 Pascal second. We are given the density to be 950 kilograms per meter cubed. We are given the volumetric flow rate to be 10 meter cubed per hour. I am going to do a nice conversion here. We know that in 1 hour we have, therefore, if you put this or punch it into your calculator, you should get. We can assume that the speed at point 1 will be the same speed at point 2, and we know that speed can be represented using volumetric flow rate over area. This can therefore be further substituted to say representing area as pi diameter squared over 4. And if you punch this onto your calculator, you should get 1.458 meters per second. Okay, now that we have written for ourselves everything that is given, step 2 will be to calculate the Reynolds number. Reynolds tells us that density, speed, diameter over viscosity. And if we substitute, we should get 136.432.35. This is definitely falling within the turbulent flow. Different textbooks might give you different dimensions, but the one that I'm using says this is turbulent flow because it is greater than 4,000. Step 3, in order to determine the friction factor, we have to take into account the relative roughness over diameter ratio. And we are given this as 0.000045 over 49.25 times 10 to the power of -3. This should give you 0.00091. If you use the the Carlson chart, at this relative roughness ratio of 0.00091 and the Reynolds number, you should get roughly estimated a friction factor of 0.028. Step 4, let's get the total length. We are going to represent it as sum of length equivalent. Now, when it comes to this step here, we have to take into consideration the major losses. And the major losses can result in when there is a significant in the flow patterns and they are changing due to size of the fittings, pipelines, valves, which can cause our fluids to contract, separate, cross-fork. So we are basically taking into consideration all these factors. Sum of the length equivalent can be equated to the 5 standard elbows that we are given, the 2 ball valves, 1 gate valve, the length of the pipeline, which is 50 meters. Mind you, we are given the values of the standard valves in a form of length over diameter. So we are given 5, we are given the length over diameter ratio, and if we multiply by diameter, we should get it in its meter form. Same thing here. We are given the 2 ball valves in the form of length over diameter ratio, and if we multiply this value by the diameter, we should get the value in the form of its length. Similarly for the gate valve, I'm just going to substitute. For step 5, we now have to calculate the friction loss, and taking into consideration that different charts have different formulas. If you read your friction factor from the Carlson chart, then you would use this equation here: 8 friction loss length equivalent diameter speed squared over 2 gravitational acceleration. If you read your friction factor from the fanning friction chart, then you would use this equation to calculate the loss of friction. And if you read your friction factor from the Moody chart, you would use this equation here. Since we used the Carlson chart, we'll use this equation here. And if I substitute, I should say 8. We calculate the friction factor to be 0.0028 with a length of, the length here, if you punch onto your calculator, you should get 61.18 meters. Therefore, the length is 61.18 over a diameter of 49.25. We have a speed of 1.458 meters per second, all over 2 gravitational acceleration, which is 9.81. And this should give you 3 meters. Step 6 will be now to substitute into our Bernoulli equation. If we substitute everything into our equation, if you punch this onto your calculator, you should get the pump head to be 19.73 meters. I hope that makes sense. It was indeed a long step, but anyways, thanks for watching.